All right. Hi, everybody. Today we are going to start Unit 7. Unit 7 is about exponential growth and decay, which is a way that things grow or shrink over time. And so this is one of those kind of real world things that happens that we can use math to explain. Some of the examples of this are population growth and decay. So when a group of people, over time, that group of people, the number of people who live in a certain area or something, that might grow exponentially or it might decay exponentially depending on if people are getting older or if people are young and are having children, etc. Some other things that you can do with exponential decay is model radioactive decay, which is kind of a chemistry, physics type of thing. And then the other big and probably the most important one that you need to know about is about interest and how interest grows over time. And when I say interest, I mean the money that you have maybe in a bank account or maybe a loan that you're borrowing and you have to owe interest on it because that's how the bank makes money, stuff like that. So we'll get into all of that this unit, but I just wanted to kind of start this unit with these are sort of the real world kinds of problems that you're going to see throughout this unit and all that stuff. There are three really big important formulas for you to know, and they're on the screen already. Two of them are more important than the other one. So all of these are what's called compound interest formulas. And so I guess I should underline those, underline. Okay. The words compound interest just means that not only are you getting interest or results or decay or growth on the original money that you put in or the original population that you start with, but it also is affected by over time. Once the account starts growing, then you get more money because there's more money in it to base your interest off of, etc. Kind of a confusing concept, but we'll talk about that a little bit more as we get into it today. What I would say is that the first two here are best used for money problems. So I'm going to write the money symbol, the US dollars symbol. So I would say this is having to do with money problems. Not like I don't have enough, but like questions I might ask you about money. This is the time, this one right here says if you get interest that accrues means you get the interest that accrues once a year. The next one over here is compounded n times per year, and this is probably the most common kind of compound interest. Your bank will say, we'll give you a checking account or a savings account where every day you get a little money, or every month you get a little money, or every week, or every year, or every quarter. So once every four times in a year, that could happen. So this is the typical bank account structure. So like usually when I see this, that's what I'm thinking of. But this also happens with loans. And so I'll try to talk a little bit about what loans look like, or, really a loan is a credit card too. So we'll look at those kinds of things this unit too. The continuous compounding interest one is for continuous growth or decay. And so this is an example where we would usually use this for things like population or radioactive decay. And a lot of other things that are not growing money-wise, but growing all the time. I said that there were two that we really need to focus on, and that is these two. Oops, there we go. These two, this one and this one. They just are the more common ones, and they're the ones that are really more applicable to real life types of problems. If I were you, I would pause this video right now and I would take a screenshot of this screen. I would maybe even go back a couple of seconds and take the screenshot of me talking about what each of these ones were, so that you have access to that in the future. I know we haven't even started talking about what the things in the formulas are and everything, but I just wanted to say that if I give you a percent, which has this symbol right here, I need to make sure that you are changing it into a decimal, because a decimal is the way that we can use this in the formulas. I wanted to just review that the word percent means out of 100, out of 100. And so if we see the word if we see the number 6.2 as a percent, what that means is 6.2 out of 100. And 6.2 out of 100 is 0.062. It is not just 6.2. So we need to just remember that the word percent means out of 100. Okay. In all of these formulas, R is going to be a growth rate, and we're going to use the decimal, which is this kind, not the one that has the percent symbol. So just be careful and pay attention to that fact. Now what I want to do is I want to go through each of these formulas and talk about what each of the letters means so that you know what I'm talking about when I start doing some problems. And then I want to compare how these all kind of work similarly, but they're a little different at the same time. The first thing you need to know is P. P is called the principal, and that means the starting amount. So that could be the beginning population of a number of people. That could be the amount you put into a savings account at the beginning of the process. R is what we call a growth rate. And I suppose I should say growth or decay rate. We'll investigate when it's growth and when it's decay later this year or this quarter. But it is a growth or decay rate. Make sure that this is not a percent. Hopefully I've said that enough times that you know that I mean it. We have to be careful that we don't write our R as a percent. The last number or the last letter here is T, and T is time. So I'm going to just kind of draw that up here. Time. It's usually in years, but that context can kind of change depending on what the question is saying. And so that's how you figure out, okay, after 8 years, how much money am I going to have in my account? Or after 24 years, how many people will be living in this area? Okay, this A over here is called the amount. And I'll say the amount you have after T time. Because if the inputs are the T's, which is the time, then that means that the outputs are going to be the amount you have after that number of time periods, whether that's years or that might be months or days or seconds or whatever. Let's use this annual compounding interest formula one time. Like I said, this is a little bit less common than the quarterly or monthly or daily compounding, but it is important that we see it, at least one example, because it is a possibility that you might see this at some point in your life. This says, how much will an investment of $1,000 at 3% annual interest be worth after 25 years? So we're given a starting amount, which is P. We're given a interest rate, which is in a percent. So we're going to have to be careful and turn that into a decimal. And then we're given our time, which is 25 years here. So what do? We put these numbers in. So we're going to say A equals, well, 1,000 times 1 plus our R is 3%, which means 3 out of 100. And if I do 3 divided by 100 in my calculator, I get 0.03. That's my R. That's what I need to use as R. And then I'm going to keep the T here because this is kind of the model. This is the relationship between money and time. So T is our time. And then what we're going to do is we're going to put that number in there. So A equals 1,000, 1 plus 0.03 to the 25. Okay, so I just have to move this over for a second. So I'm going to type in exactly what I see here. I see 1,000 times the parentheses 1 plus 0.03, close the parentheses, and then to the 25 power. And then hit enter, and then your answer is 2093.78. So I'll just write this down really quick. My answer is $2,093.78. Okay, cool. So that was yearly compounding. Let's talk about when we compound the interest more than one time per year. And what that means is the bank is just doing the calculation for you more often than one time per year. Sometimes banks will do it once per year, but other times a lot of banks will do it either monthly or 4 times a year, which is called quarterly, or daily, which is really common. Okay, so let's take a look at this. We have compound interest compounded more than once per year. Again, our P is our principal. Our R is our rate in a decimal, not a percent. Our N is our number of times per year. Number of times per year the interest is compounded. Okay, and then T is still time. And especially with these money problems, T is usually in years. This question is saying we deposit $1,000, again, same deal, into an account that returns 1% annually. So our R is 1 per 100, or 0.01. And then compounded monthly, well, there are 12 months in the year, so we're going to write N equals 12. Okay. And then we see, okay, you deposit $1,000 into a savings account, so P is 1,000. And so then the question says, how much will there be in 18 months? How many years is 18 months? Because T is in time, which is in years. But then it says how much money will be there be in 18 months. Well, 18 months is a year and a half. So this is 1.5 years. And then we're also going to be using 5 years. So it's asking us two questions. So it's asking us to do the same thing twice. So let's write our answer, our model. A equals 1,000 times 1 plus fraction of 0.01 over 12 to the 12t, and t is going to be the thing that we're changing. That's the thing we're going to be putting in 1.5 and 5 for. Okay, so to do this in your calculator, I have to zoom out a little bit so that you can see it a little better. And I guess I kind of cut off the first part here, but we're going to type in that same 1,000 times 1 plus. This is the tricky thing here. I'm going to go back a second. I'm going to press this green button alpha and then the y equals button to get a fraction and then hit enter. That allows me to get a fraction, and then I'm going to type in 0.01 divided by 12 to the 12 times 1.5. And I got my answer was $1,015.11. What I did next here is I was able to copy, so I'm going to go back for a second. So I got my answer, and then if I go up and copy it, so I hit enter again to copy that down, then I can just edit the formula. So I can delete the 1.5 and retype the 5, and then I'll get my answer here. So it was 1051.24. So I'm going to write that. In 5 years, it was 10.51 and 24 cents. The next formula you need to know is about continuous compounding interest, and this is the one that we use the most for things that are not money. So this is like populations or bacteria or maybe radioactive decay, something like that. What this means is that the thing, whatever we're measuring, is growing or decaying all the time. So it doesn't go step by step by step like the money was in the last couple problems. This one is happening at all times. So it's happening really smoothly. On this slide, it just says that P, A, R, and T are all the same things. So P is still principal, starting value. R is still rate. T is still time. And A is still amount after whatever T time you have gone through. The thing that is new is this number called E, and it is a number. I know that it's written as a letter, but E is about 2.718282, and I'm encouraging you to use the button that says E on your calculator. I'll show that to you in a second. So to get E, you're going to press the second button, which is that blue one on the top left corner, and then you're going to press the divide button to get E. And then if you hit enter, you can get the same decimal approximation as what I said it was on the slide. I want to spend a little bit of time comparing annual compounding interest, quarterly compounding interest, monthly compounding interest, and continuously compounding interest. We're going to use sort of that, we use this example already, but I want to use this example where we have a P equals 1,000 and an R equals 0.05. These are the spots where we're going to be changing N, and then we're going to be changing which formula we're using here. So this one in annual compounding, we're going to be using A equals 1,000 times 1 plus 0.05 to the T. Over here, with the quarterly compounding, we're going to do the same formula, except it's the one that has the N's in it. So 0.05 is the same, divide by N is in this problem, it's going to be 4 because there are 4 quarters in a year, to the 4T. Okay, the next one is the same, except we're going to change the 4 to a 12. Like that. And then the last one, this is where it's different. A equals our 1,000, and then we have that E number to the R, which is 0.05, and then T is green, like that. Okay, so I'm going to do one example of doing each of these in my calculator so that you can see that, and then I would like you to finish these. Okay, so P is 1,000 times 1 plus 0.05 to the 2, because that's what the first year says right here. Okay, the next one I'm going to do the same thing, 1,000 times 1 plus, and then this time I'm going to need that fraction. So alpha y equals, and then the enter button down there. And then I'm going to do 0.05 over 4, because it's quarterly compounding, to the, 4t. And t is 2 in this problem. So hit enter. There it is. The next one is, hold on, I have to erase. 1,000 times 1 plus, again, I need that fraction, alpha y equals, and then enter. 0.05, and then divided by 12 this time, because we're working with monthly compounding, to the 12, and then 2 is t. Okay, good. And then the last one is 1,000, and then I need that e, so second divide, and then to the 0.05 you can either use parentheses or multiplication, and then there's your answer, 1105 and 17 cents. So I want you to finish those. So you might need to get your TI-84 out of your Chromebook out and get those done. Type those in on the next slide. There's going to be a draw it where you're going to be able to put those in, and then compare your answers against mine. At the end of all of this, these are the answers you should have gotten. It's not a huge deal if you're a little bit off, but we do want to try to be accurate if we can. What I really want to focus on is, and I recognize that over time, you know, nobody's really going to let 100 like this kind of money sit in 100 in an account for 100 years, but the differences between these is pretty significant, especially between these two is a really big jump, and then between here and here is a little bit less of a jump, and between here and here is also a little bit less of a jump. And over 100 years, like the difference between, you know, $3,000 is not that much over 100 years. So if you kind of think about it like that, but, you know, it's still important for us to kind of see that there are differences between these formulas and that we have to be careful about which one we're using. Okay, so the big things that you need to know are that we can model exponential growth and decay. We haven't done any decay problems today, but we will in the future. We can model exponential growth and decay using lots of different contexts, including money and populations and other types of things. We've really only focused about money today because it's the most important thing. Just kidding. But so yeah, there are 3 formulas you need to know. They're on this screen. And then there are kind of lots of different ways that we can use this information to apply it to our lives. You have some practice problems today and not a mastery check to practice figuring out which formulas are appropriate, putting in the values for the time, and then getting out your answers and using them to approximate some things.